Wow, guys, did you see the shot he just made? Look at that arc!
Alp, what's the area underneath that arc?
Wow, that's a really good question. I wonder how I can find that. The backpack! AP stats? That's no good. Oh, now that's the book I like. Alright, now to find the curve. What could be the curve of that shot? Do you guys think it's a linear curve? What about a quadratic curve? Yes, you got it right. Alright, so now, if it's a quadratic curve, what kind of quadratic curve could it be? I think I'm hearing some good answers. Yes, it is a negative x squared. You guys are really good at this. Wow. Alright, so to find the area under a curve, we technically need to have two bounds. Do you guys think we could say Alp's hand could be the starting point and the tip of the basket could be the second point? That's a good idea. Let's do that. And if we say that the real area under the arc could be from the tip to the ground, which will be the x-axis, would that really work for our integral? Yes, it would. Awesome. Now all we need is the measurements. I have an idea for that. Let me take out my magic wand. Oh, this is not Disney? Okay. Ding! Wow, all the measurements appeared. Now we just have to plug in the values into our calculator. Can you do that? Great!
Alright guys, since this is such an involved problem, I'm going to need the help of my calculus friend Allison.
Hello everyone. To evaluate the integral, the first step is to determine whether it is a definite or indefinite integral. Because we need the area of the graph between two defined points, we will be using a definite integral and the second fundamental theorem of calculus, which states that the f of x is the general integral of a graph. But by taking the integral of the endpoint and subtracting the integral of the starting point, we are able to get the difference in area between the two. In this case, the equation to be integrated is negative 0.125 x squared plus 2.14 x plus 6. Because we set Alp as the starting point, we'll set him at 0. And as a result, the endpoint, the basket, will be 15. The most basic rule to evaluating the integral is that x to the power of n integrated is x to the n plus 1 divided by n plus 1 plus c. Now, c is a constant that we add to stand in for any constants that the original function was unable to show. Another integration rule is that the integral can be split up. So in this case, z is another constant. And that would become the integral of x plus the integral of z. So using those two rules, we'll now integrate our own equation. So that becomes the integral from 0 to 15, negative 0.125 x squared plus 2.14 x plus 6, integrated in regards to dx. So splitting that up, that's 0 to 15, negative 0.125 x squared dx plus 0 to 15, 2.14 14x dx plus 0 to 15, 6 dx, which becomes negative 0.125 x to the third divided by 3, because this is 2 plus 1, and this is 2 plus 1, from 0 to 15. And we do that for all of the rest of them as well. Now all that's left is to take the area of the of the end value, which is 15, and subtract it from the area of the start value, which is 0. Because 0 entered into each of these equations equals 0, we are only subtracting 0 from each of these. If you plug this into your calculator, it becomes negative 140.625 plus 240.9375 plus 90, which equals 190.3125 feet squared as the area underneath the arc.
Oh, that actually makes a lot of sense. Thank you, Allison.
Wow. Alright, so from what I can see, the arc looks just like the one we did in the first question. But this time, this other handsome guy is running towards him, trying to block the shot, and he's really going for that block. That looks like a horizontal line to me. Would you agree? No? Yes! Thank you! It does look like a horizontal line. And if we assume that this one works again to get our measurements. Alright. Now we got the measurements of the horizontal line. Alright, so now if we want to find the area between the two arcs. Well, we can see that the shot curve is definitely has a larger area under it than the blocking line. So if we put Caleb's shot first in the integral, and from that subtract Alp's running line area, we should be able to find the area between the two lines. Alright, I think you guys can plug it in the calculator, right?
On this second problem, we will be taking the integral between two lines. The second problem is very similar to the first, and so as a result, the upper arc will stay the same. As you'll recall, negative 0.125 x squared minus 2.14x plus 6. The second line, a horizontal line following Alp's hand, we'll call y equals 6. Just like in the first equation, we will take the integral from 0 to 15, once again making this a definite integral. When you take an integral, you find the area under the curve. For example, in our last problem, we took the area under this curve, from 0 to 15. And the integral of y equals 6 would be this area. Now, to find the area in between, we must do just as we did with the start and end points of the definite integral, subtracting the total area at the end point from the area at the start. This time, we will take the area integral of the first line and subtract the area of the second line, giving us the difference of the areas, or the area in between. So the integral would be 0 to 15 negative 0.125 x squared plus 2.14x plus 6 minus 6 dx. And as you recall from our last problem, we know we can split the two equations, making it 0 to 15 negative 0.125 x squared plus 2.14x plus 6 dx minus 0 to 15 6 dx. Now I made a mistake in my last equation when I wrote it down. The integral of the first equation is negative 0.125 x to the third over 3 plus 2.14 x squared over 2. 2.14 is in fact not divided by x squared. Plus 6x from 0 to 15 minus 6x from 0 to 15. Now from our last problem, we'll remember that this area came out to be 190.3125 minus 6 times 15 minus 0, which would be 190.3125 minus 90, making the area between the curves 100.3125 feet squared. Thank you very much.